Hey everybody, I'm excited to share with you the next episode in the Root Finder in Space series. This episode ran a little bit longer than usual. It's got a total of about half an hour. In addition, there was an interruption in the middle. I got a phone call in the middle of the episode, which sort of naturally broke it up into two 15-minute chunks. So I'm uploading this episode as two separate videos, episode 6A and episode 6B. I'm uploading them at the same time, but I'm splitting them up just so that you're not having to stare at my coding for half an hour straight. So anyway, hope you enjoy it. On with the show. Hello and welcome back to Let's Code Physics. We are in episode 6 of our series on finding the minimum aphelion and perihelion of a planet's orbit around a star. We checked our code last time by putting in the values for the Earth going around the Sun. So we put in the mass of the Earth, the mass of the Sun, a period of 1 year, an appropriate value for G, and we ended up with the accepted values for the minimum aphelion and perihelion for the Earth. So we've shown that the code works. Today what I want to do is take a look at some physics that we haven't observed in our universe. We haven't observed yet, I guess I should say. So gravity acts according to this potential energy. The important thing is that it goes like 1 over r. One of the neat things about computational physics is that you can explore other models. So for example, we can change the functional nature of this potential energy here. And that's what we're going to do today. So we could come up with any number of potentials to put in here. We could do a decaying exponential. We could do a Hooke's law force. We could do all kinds of stuff. But what I think we're going to do today is play around, keep the same general form for this, but play around with the power to which this R here is raised. So right now it's being raised to the first power. So we're going to generalize that by raising it to just a letter P, or variable P, I guess I should say. We're going to revert back to our standard values here for just 1. So we're not worried about the Earth right now. And what I want to do is I want to be able to change the value of this power here in order to see what kind of different results I get. So we've been working with a power of P equal to 1.0. And so if I just make these changes to the code, I'll get the same kind of results that I got before. I get a minimum right at 1, an aphelion of 1.8 and some change, and a perihelion of 0.69 and some change. So that's what we've been getting. Those line up with our energy value of negative 0.4. So this is working out well for us. But what we would want to be able to do would be to change this. So like, for example, let's suppose the universe were off a little bit, or our laws of the universe were off a little bit, and this were actually a 1.5. That's going to change the nature of this potential here. It's going to change the nature of the function that our code is evaluating. So if I run it again, I'm going to get different values. So the minimum is still at 1. So that might be a universal feature of this format. That would be something we can investigate. But you notice that the aphelion has moved closer and the perihelion has moved farther away. So these two numbers have actually gotten closer together. So if we were to graph this with this power of 1.5, we'd see those two intersections getting closer together. So that's kind of an interesting feature. So for example, we could change this to any value we wanted to. We could change it to 1.75, and then we get a pretty similar value for the perihelion, but the aphelion is getting closer in there. I do want to be cognizant of the fact that we may need to change these bounds. So actually, let's go ahead and maybe bump this down a few orders of magnitude and bump this up a few orders of magnitude. That's not going to change the answer we get. As you can see over here, it just changes. Oh dear, that did change the answer we got. Well, maybe I needed to worry about that beforehand. This is why you should always graph things before you get started. So actually, how about I take a second here and do what I should have done before and graph this thing. So I'm going to open up GNU plot. Sorry, I try to keep my start menu hidden from y'all just so you don't get too distracted. But maybe you like seeing my start menu, who knows. So let's try plotting this thing. Actually, let's set the X range first. I always forget to do that first. Let's go from 0.05 to 2. And then we're going to plot this function. So this is 1 divided by 2 times x squared minus 1 divided by x to the 1.75 power. Is that the thing I want to plot? All these things are equal to 1. So this is a 1 divided by 2 times independent variable squared minus 1 over independent variable to the 1.5 power. Okay, this is what I want. Okay, so what I notice is that at the, I should also plot my energy value. My energy level is negative 0.4. So let's recall that command. And now, actually, I don't need parentheses around plot, do I? I don't work in GNU plot all the time, so I have to remind myself of the syntax and everything. Let's put in negative 0.4 for good measure. Okay, so this thing is pretty close to where this thing starts to level out. So I might want to lower that just for demonstration purposes. But what we can see is that this intersection is way, way over to the left here, so about 0.06 something, which is what we were getting here. So that value was not being accessible when I had the bounds smaller than that. So let's actually make this thing extremely small. Let's go ahead and make this thing another order of magnitude bigger. Again, the advantage of this sort of divide and conquer approach to finding an intersection is that you can increase the bounds by an order of magnitude. It really only adds, a couple of iterations. Let's see. So this is still coming out fine. Our aphelion has stabilized. Our perihelion is stabilized. So that is good. So what we could do, we could play around with this a little bit. Try out different values of P, but what would really be interesting would be to see how these outputs vary with this input of the power. And so we could do this manually, changing it, one value at a time and then tabulating the results. But we have a computer here, and computers are good at doing the redundant stuff for us. So I'm going to set up another loop. I'm going to wrap this whole thing in a loop. Scilab is kind enough to give me an end there, but I don't want to do that. And I want to go from P equals 0.0. Why don't we start at 2? And let's go in steps of 0.02 up to, let's broach up to 1.8. I'm a little wary of going up to 2 because when I was trying this code out earlier, strange things were happening when I had the power equal to 2. But maybe I should have graphed it first, so I'm doing on the recording what I should have done off stage. So I don't need this statement anymore because this for loop is now controlling what the p-value is. But what I do need to do, if I want to graph these results later, I need to store my p-value. I'm going to put that in an array called power. And of course, I have to tell it what IP is. So let's give an initial IP of 0, and then at the beginning we'll increment IP by 1. There we go. So I'm going to have one array for the power. I'm going to need another array for this first result, the minimum. So let's go down to where it calculates the minimum. And I'm just going to leave the print statement in. It'll put a lot of text on the screen here, but it'll go by pretty quickly. Let's create an array r minimum, that's good enough. R minimum is fine. Our M&M. Today's episode of Let's Code Physics is brought to you by M&M's, now in radial flavor. I hope I don't get in trouble for that. So that's now going to be our minimum value, our middle. So that's fine. Let's scroll down. The next thing we need is the aphelion value. So let's store that in an array aphe. I don't know anybody or any company named Aphe, so I can't continue my jokes of today's episode is brought to you by. Let's see, and then down here is the perihelion, so let's call that array peri. Today's episode of Let's Code Physics is brought to you by Peri's Periscopes, and that's going to be our mid. that might be all the jokes I got for now. That's what I'm thinking at this point. And let's hit save. And of course, we started a for loop. We need to type in end. And Scilab is nice enough to tell me that I got the wrapping correct through the pink shaded area there. And just for good coding, let's select all, and I guess that's correct indentation that I want. There we go. So everybody is now indented appropriately. All right, so we're going to wrap from p equals 0.2 to 1.8. The only thing I'm concerned about is this rmin and rmax business. That's the leftmost bound and rightmost bound that the code is going to search. So we are going to execute code intelligently here, and we're going to try out a power of 0.2. That's what we're starting at, right? Let's hit that plot. Okay, if I zoom in here, oh my, I don't know. Let's expand the X range a little bit here. Let's go out to 200 like we're planning to do. Replot. Oh, that's not actually that's getting it looks like it's intersecting here and then out here somewhere. Okay. So our 0.2 going out to 200 ought to be okay. That's like marginally okay. So let's, we've got 2000, so that ought to be fine. And then our other intersection is somewhere over here. So let's check that out. So this intersection is somewhere around, it's somewhere around 0.9. Okay, so we're fine with a quadruple 1. The other extreme, we want to check out 1.8. So let's have this thing plot this to the 1.8 power. Oh my, that drastically changes matters, doesn't it? Let's reset our X range and replot it. Okay, so the minimum is actually really, really close here. So actually what I want to do is zoom in really, really close. So I want to go from 0.001 to, looks like I can safely go all the way out to, say, 3. Go from there to 3. Okay, so this intersection is somewhere over here near 0.03, it looks like. Let's double check that. Let's put in a 0.02. No, that didn't work. Oh, you know what I just need to do? I just need to set log scale X replot. There we go. All right, now let's put this thing back to rights. Let's put this back out to 3. Okay, so now I can easily see that from 0.01 ought to be fine. Okay, so this might have been a little bit of overkill, I'm thinking. So when I plot, let's see, so this is where I have to keep track of a few numbers. So 0.01 out to wherever is fine for the 1.8 extreme. What about the 0.2 extreme? Log scales are your friends, folks. I'm not even joking about that. Put this out to 300. Okay, yeah, cool. Okay, so, all right, let me go back to the 1.8. Okay, yeah, so the 0.01 ought to be fine. Let's go 0.0001 just in case. Okay, we're going to save. And now we're going to run, and this thing is going to give us a whole bunch of different power values. We will see how long it takes. And it didn't take that long at all. What strange results await our hero as he plays with the very laws of nature itself? Find out next time on Let's Code Physics!